Hello, everyone. Good morning. I'd like to just start with a brief introduction. This is a session on gravity waves in the atmosphere and ocean. My name is Joan Alexander, and I'm co-convener with Jeffrey Chagnon and Paul Williams. And we have a wonderful list of talks here today, but I wanted to also mention tomorrow morning, in the 8 to 12 block, there's a poster session on this topic. Lots of really wonderful posters. There are wonderful contributions there that we couldn't make room for in this schedule because, as you know, most of the presentations are poster at the AGU. So I hope you'll all come to that. It is between 8 and 12 is scheduled for that, but we thought it might make sense to try to cluster in the first half of that poster session, so the first couple of hours. So that's just a suggestion. It's not necessary, but I think it's maybe, at least I know Jeffrey and I will both be there in the first couple of hours, focused on that. Okay, so now I'd like to introduce Jeffrey, who will introduce our speakers.
Okay, good morning. Thanks for all arriving at such an early hour. I hope all of you have a lot of caffeine in you by now. Just a brief announcement for speakers, some directions before you start. There are some lights up here on the top of the podium. For the first hour, each speaker is allotted 15 minutes. When you get to 12 minutes, you'll see a yellow light come on, and that'll warn you that you should probably finish up in the next few minutes. If it goes red, that means you're out of time, and unfortunately, we'll have to move on to the next speaker and skip the question and answers. Also, this is one of the sessions that is being recorded for the video on demand, which means that you'll have to speak into the microphone, so try and remember not to walk around too much. And during the question and answer session, it would help very much if after the question is posed, you could repeat some part of it into the microphone. Okay, does that make sense, I hope? It will do when we begin. So our first speaker this morning is Bob Sharman. The title of his talk is Gravity Waves and Gravity Wave Braking as Contributors to Aviation Turbulence, with co-authors Lane, Treyer, and Fauvel.
Okay, thank you, Jeff. And I'd like to start by thanking the conveners for inviting me to give this talk and acknowledging my collaborators, some of whom are listed there. Let's see. Advance the screen.
Make use of this mouse.
Okay. Okay, we can do it that way.
Sorry about that.
That's all right. First, some background and motivation. For 10 to 15 years now, I and others have been working on developing techniques to forecast turbulence for aviation purposes. And for aviation purposes, what we really are interested in is certain scales of eddy sizes, somewhere between tens of meters and a few kilometers. Scales larger than that, the aircraft does not respond very well to, tends to ride out the waves. Smaller scales don't affect the aircraft hardly at all. There are some situations where this turbulence can be rather severe. If you can see that image on the upper right, that's a DC-8 cargo plane that hit extreme turbulence over the Colorado Rockies in 1992. So extreme that it lost an outboard engine and 12 feet of wing. However, it was able to land successfully at the then Stapleton Airport. The goal then is to use operational methods to predict these turbulent encounters. Operational means it's available 24/7. And you need some amount of lead time so that aircraft can plan to route around that turbulence. So basically we're left with using numerical weather prediction model output, which is operational and is available 24/7. However, because of the grid spacing of those particular models, we cannot actually resolve the eddy sizes that are responsible for turbulence. So we have to infer it some ways. They do capture the large scales, and assuming there's a downscale cascade of energy from the large scales to the small scales, we can infer aircraft motion from the large scale forecasts. So the procedure basically is to diagnose turbulence potential based on some semi-empirical relations, which we call diagnostics or Ds, from this NWP model output. Currently, we've developed a system that uses an ensemble weighted means of these diagnostics. We call that the Gridded Turbulence Guidance Product, GTG, and there's an example output. What you see in the output is contours of turbulence levels in the light and moderate category. For verification and for further study of turbulence episodes, we have routine verbal pilot reports, PIREPs. And I'll talk more about that in a minute. And lately we've developed this automated eddy dissipation rate reporting mechanism that estimates eddy dissipation rate at basically 1 minute intervals, and the pilot doesn't have to do anything. For operational purposes, having a moderate or greater PODs of 0.85 or greater and false alarm rate less than about 15% is the goal, and we're just about there. There has been recent understanding in the nature and causes of turbulence in clear air in the upper troposphere, lower stratosphere. These have been from more accurate observations like the eddy dissipation rate estimates that I've talked about earlier. The pilot reports sometimes tell us a little bit more about the event, and we can get a clue of what's going on. But by far the biggest boon to this has been nested numerical simulations of observed events where the grids are large enough to capture the large scales that are responsible for the event, and yet have a grid spacing that's small enough to capture at least part of the motions that are directly responsible for the turbulence. These studies have shown that gravity waves and gravity wave braking are an important contributor to the turbulence. And the most important contributors we found so far are mountain wave turbulence and convectively induced gravity waves, which lead to turbulence outside of cloud. And we call that near cloud turbulence. Of course, there's other processes that generate gravity waves and could lead to braking as well. Adjustment processes and shear instabilities are a couple of them. Here's an example of a mountain wave encounter over Greenland. These are traces from the flight data recorder. On the upper diagram on the left, there is wind speed is the dashed line, and the solid line is temperature. You can see that preceding the event, there's definitely a wave of about 40 kilometers wavelength. If we focus in on that event in the lower image, now it's vertical acceleration in the dark lines, the heavy lines, and the dotted lines are the vertical wind. We can see that now those large-scale waves have given way to smaller scale waves on the order of 4 kilometers or so. So the breakdown process is fairly complicated, but it does look like waves of fairly short wavelength were a precedent to it. Nevertheless, Jim Doyle did a simulation of coamps of this particular case, and that image is on the right. And you can see that the subgrid TKE did show turbulence at about the right position and about the right time. The incident is where the red circle is. The green contours are elevated TKE. So in spite of the fact that that was a 5-kilometer horizontal resolution or a 5-kilometer grid spacing, it captured the event pretty well. But there are a lot of wave reports we get with these pilot reports, and a lot of them actually are not over the mountains. The image on the left here is all the pilot reports that say wave in them. That is, they say we had turbulence and we also hit waves. And you can see that, of course, there's a lot of those reports over the Colorado Rockies, Cascades, and Sierra Nevada, but there's also a lot of reports over the Great Plains. So what's going on there? There certainly isn't topography. One of the things that is going on there is that there's convection, and convection can lead to gravity waves. And these gravity waves can propagate above the storm, as in this example here. This is a case that was based on an actual encounter in 1997 over Dickinson, North Dakota. The aircraft was flying over the thunderstorm and hit severe turbulence with 22 injuries. You can see the gravity waves propagate vertically away from the storm as the storm starts to penetrate the tropopause. And you can see that these gravity waves propagate very high above the storm. They break. The regions of breaking are indicated by the red areas. And so this process turns out to be quite common. We looked at this in a little more detail to determine the sensitivity of this process to shear and stability above the cloud top. And we get something like this. As you might expect, the results do depend on the shear and stability above the cloud top. And this is significant because the FAA gives guidelines for aircraft flying over the tops of thunderstorms. And all they mention is the wind speed at cloud top. So the effect of shear and stability is completely missing from those guidelines. Here's another case of near cloud turbulence. Each one of those little dots on the left-hand side image are these EDR reports, so you can see how many of them. They're a minute apart. You can see that there's tracks all around this storm, but in fact there is only severe turbulence indicated by that red dot and moderate turbulence by the orange dot to the southeast of the storm. And you can see that in the radar image as well. Here's an animation that Rob Foville did of this particular case. It's a 1.5 kilometer grid spacing. You can see that indeed to the southeast there's lowered regions of Richardson number, and you can see that waves tend to be propagating to the southeast, away from the storm. And here's a vertical cross-section through that southeast plane that was indicated on the previous slide. And again, you can see the gravity waves propagating away from the storm. And I don't know if you can see the contours of Richardson number as the black lines, but the Richardson number contours are a minimum at that particular flight level where the turbulence was experienced. This is a common effect, and you can demonstrate this to yourself. This is simply a linear gravity wave, a mountain wave, set up by flow over topography. Stability and shear are constant, so the upstream Richardson numbers are constant. You can see that this sets up a train of trapped waves in the W field, but it also perturbs the Richardson number, so that this mean Richardson number of 8 is increased in places to 32 and decreased in places to 3. So we think this is an important contributor to reducing the Richardson number so that turbulence can happen. I think I'll skip this slide because we're short on time. Here's another situation where turbulence was observed in the clear air around a thunderstorm, but in the cold air behind the thunderstorm. I don't know how well you can see that, but there's 2 clusters of reports of turbulence, one in northern Illinois and another in southern Illinois. And we looked at this case in detail with WRF simulations, and incidentally there were some pilot reports that indicated there was wave motion associated with this event as well. So at the lower right, or lower left rather, is the results of the simulation in a north-south cross-section. And this are contours of the V component of velocity and contours of TKE. And again, you can see the reports. And the reports cluster in regions of very high shear. Those red contours are TKE from the model. But there's also a cluster of reports above the low-level convection. And you can see some evidence of gravity wave motion in that upper level around the reports. Interestingly, we ran this simulation again without convection, turned off the microphysics, and you get the resulting diagram on the lower right. And now you can see the shear is gone. There's no gravity wave motion because there's no convection. and actually there's basically no turbulence at all. So in this particular case, even though the turbulence occurred in clear air, it really wasn't classical clear air turbulence. It was due almost entirely to the presence of convection. If we take an east-west cross-section through that storm, again, you can see the low-level convection, and you can see the upper-level convection, and you can see the low-level convection generating gravity waves that are propagating vertically into the flight levels. So again, at least based on this case and some others we've been looking at, that clouds, even in the wintertime, are essential for understanding and predicting where turbulence is going to be in clear air. In summary, I'd say that recent advances in understanding aviation turbulence have been forthcoming, and they're due mainly to computer simulation capabilities increasing over the last 10 years or so, that we can do these simulations that have a domain that's large enough to capture the large scales and yet has a grid spacing small enough to capture turbulence or motions that are directly related to turbulence. And we do have these more precise observations in the form of these eddy dissipation rate estimates that are automatically generated by some commercial aircraft. We're also finding that CAT is not so simple, that turbulence in clear air is often really associated with convection, in particular near cloud convection. We see that outflows enhance the shears, they lower the Richardson number therefore, which in turn affects gravity waves and gravity wave propagation. Existence of critical levels are important. That was a major contributor to turbulence in that above cloud case that I showed you. Another major point here is that gravity wave perturbations can reduce Richardson number sufficiently, and especially in regions where the Richardson number is already low, to generate Kelvin-Helmholtz instability. We're starting to look at pilot reports more carefully because they're very useful in identifying conditions where turbulence occurs, and especially that may be related to waves. We intend to follow this up with some high-resolution simulations of those cases. From the forecasting perspective, the major research areas are then identifying gravity wave cases that are related to turbulence and develop better parameterization for gravity waves and gravity wave breakdown and how they lead to turbulence. Thanks.
Okay, thanks very much. Okay, in the interest of time, unfortunately, I think we're going to have to move on to the next speaker. Thanks very much, Bob. Our next paper our next talk is by Kurt Poulsen, who will be speaking about stochastic closures for finite amplitude internal waves with co-author Lvov. I hope I pronounced that correctly.
Thank you. Yes. All right. I would like to thank the conveners for the invitation and the turnout in the early morning by the rest of you. There's a potential change of title here from stochastic closures for finite amplitude internal waves toward strongly nonlinear closures for stochastic internal waves. The difference is that you can have a weakly nonlinear theory for finite amplitude waves as opposed to a theory that does not make an assumption about weak nonlinearity. And if you understand that distinction, then this is what the talk is oriented to. I tend to do a lot of my thought process in the spectral domain, and so here, you got a pointer? Okay. All right, so what we have is diagrammatically is a shear spectrum is a function of vertical wave number. And in the ocean, you tend to have 1 to 2 orders of magnitude in vertical wave number space, where you have power laws, with the canonical power law for a shear spectrum of being white, or m to the 0. And we talk about kinetic equations and ray tracing models for models of nonlinearity in this regime. And when you get out to high enough wave number, the shear variance is large enough that you hit a saturation by shear instability. And when you go to the atmosphere, There's also this -1 parameter regime, but the last time I checked, the discussion was about Doppler shift ideas and in competition with saturation. The point, one of the things that was true at that time is that the amplitude in the ocean of this -1 regime was larger than the amplitude in the atmosphere. And so what I have to say about these non-instability mechanisms, these wave-wave interaction mechanisms up here in strongly nonlinear parameter regime may be pertinent to this Doppler shift ideas. So, no? That one. Okay. All right. So in the formal paradigm that's going on here is I'm working with Yuri Lvov, and he's got this nice Hamiltonian formulation in isopycnal coordinates. And you can go to, assuming weak nonlinearity, develop kinetic equations for finite amplitude waves that have resonance broadening in them. They're within the direct interaction approximation. You can make a small amplitude assumption to get the resonant interaction approximation. Either way, you're dealing with ideas about Fourier transforms in the spectral domain. And at best, what you have is an amplitude that's a function of time times a plane wave solution. And in the resonant approximation, the amplitude is independent of time, and you're trying to solve for the small tendency. What Yuri has done is assumed, so kinetic equations, you assume extreme scale separation, and you get a Fokker-Planck equation. Yuri has used as a Hamiltonian, assumed as an extreme scale separation, no assumption about weak interaction, and this basically puts you into a rate tracing paradigm where the amplitude is a function of space as well as time. It's going to use a Wigner transform to deal with the issues of spatial localization to get a Fokker-Planck equation out of this. Again, it's going to be different, and there's no assumption about weak nonlinearity in this approach. So what we have are three different Fokker-Planck equations, which then are just diffusion equations in the spectral domain. All right, so it's time rate of change of wave action n, the divergence of a diffusive flux, and the whole art is to solve for this diffusivity. What I'm going to do here is not feed you any of the theory. I am going to compare results from this Fokker-Planck equation with results from ray tracing. All right, so we wrote a review paper that came out in Reviews of Geophysics, and the first thing we did was we fit parametric spectral representations to oceanic data. So we said, energy spectra have a frequency power law, a wave number power law, sigma to the minus q, m to the minus r. We convert that to an action spectra, energy divided by frequency, in the horizontal vertical wave number domain, so it's k to the minus a, m to the minus b. And then we took all of the data and we did a scatter plot of power law A versus power law B here. So each one of these points is a data set, and for each data set there is a story about that, about where it is geographically, what the role of eddies, tides, winds might be in providing the sources for this particular data set. But what you find is there's a clustering of data sets, one down here, another clustering up here, and then there's this one following this white line, and then there's a bizarre data set up here that doesn't really group with these thick white lines here. All right, so what the thick white lines are is you go to the Fokker-Planck equation with the resonant formula for D, and you say, let's look for stationary states. Time rate of change of wave action in the spectral domain is 0, and plug in solutions of k to the minus a, m to the minus b. What are the values of a and b that give you stationary states? There are two families of stationary states. They are the white lines. One is 9 minus 2a minus 3b. It is a constant flux of action to small vertical scales. And then this white line right here is a no flux solution. All right, so that's going to kind of be key in this. All right, so those stories are in the Reviews of Geophysics paper. And the takeoff here is that, well, we also measure epsilon for many of these data sets, and we can talk about energy cascades. This no flux solution, this family down here, that means no mixing. We can go in with our turbulence probes and say, well, wait a minute. The observations say there's mixing for these data sets. So it's this clustering of data sets that's right down here. This includes the Garrett and Monk spectrum, which is the red dot that's buried back in here. And if you were to ask any self-respecting oceanographer whether the Garrett and Monk spectrum has mixing associated with it, the answer would be yes. It is the very definition of background mixing in the ocean. All right, so the summary from this Reviews of Geophysics paper was the background wave field is not universal. You go through and you say, well, gosh, there's all these power laws that are up here, so we can't just talk about Garrett and Monk anymore. There's this variability. The observed power laws are consistent with the resonant kinetic equation. Well, this is really interesting because there is no good reason for this. This resonant theory is formally invalid and it's incomplete. So there's some explaining to do here, and this is the start of that explanation is this talk. All right. When you're doing triads, kinetic equations are going to be built around, they're systems of coupled oscillators. And what you're doing is you're coupling three waves together. So you coupled oscillator springs, you got three springs. And for these power laws that I've been talking about, there's three waves. Here is a frequency, vertical wave number diagram. You're going to talk about coupling one wave with frequency near F and large vertical scale with two waves. One of the waves is up here, one of them is down there. And the resonance manifold is going to be this red line here. So one of the waves is going to lie on this red line, one of the other waves is going to lie on this red line, and this blue line here is the approximate resolution, resonance condition that the phase speed of this near inertial wave be equal to the group speed of the high frequency waves. One of the waves is just going to be slightly faster than the phase speed of the near inertial wave. One of the waves is going to be slightly slower. Okay? So you need to understand that to understand some of the results of the ray tracing. Ray tracing, time rate of change of wave number following the group. I'm just going to look at a system where there's only background waves that have vertical shear, and so I'm just concerned with the time rate of change of vertical wave number. You take this, you follow for the evolution of the wave following a packet of its wave number. The packet position is given as a time rate of change of the horizontal velocity plus a group speed. I'm going to show you results for single waves and then stochastic background. And I'm going to talk about my results in terms of 10 to the minus whatever times the Garrett and Monk energy level. Okay. Now, this single waves are, say you have a velocity profile outlined in blue of this near inertial wave. It's going up. It's got a phase speed that goes up. There's going to be small scale waves that have group velocities. One's going to be slightly smaller, have a slightly smaller group velocity, and so relative to this background wave, it's going to be overtaken by it. And so as that happens, it's going to sample the entire phase of the wave. There's a wave here that's going to be slightly faster. It's going to overtake the crests and troughs of that near inertial wave as you do the ray tracing. All right? So what I've done is here are the velocities from a maximum positive velocity to maximum negative velocity that are sampled by these two waves. One of the waves is in a solid blue. The other one is in a thinner blue solid line. And here the background is 10 to the minus 10 times Garrett and Monk energy levels. 10 to the minus 8, 10 to the minus 6. What's going on is you're sampling the entire phase of the wave, that background wave, until you hit something like 10 to the minus 4, where you start to get stuck in the trough of a wave. All right? So you go back to this diagram. What's happening is there's a wave that's propagating here. It starts to interact with the shear of the wave. It slows down. It goes back here. The shear changes sign. It speeds up, and it oscillates around the trough of the wave. So you get a bound wave phenomenon. Well, what I'm going to do now is talk about where you don't have just a single wave And I'm talking about the phase that the test wave occupies in the background. I'm going to have an entire stochastic system of waves. And what I'm going to do is I'm going to take my test wave, and when it attains a certain wave number, I am going to ask, what is the phase of the background wave, right, that it occupies? Well, there's lots of waves in my simulation, and in each of these grids, there's, in this plot, there's probably 100 different background waves. And it's an average on the phases of those 100 different waves. And what you see is that there is a phase locking here with, okay, so this axis goes from 0 to 10 here. This is my background wave normalized by what it would be if it was resonant. And so 1 is the resonant wave. Waves that are larger scale and faster, the waves get stuck in the troughs. Waves that are smaller scale and slower than the resonant wave, you see the phase locking migrate up into the crests. Now this is for 10 to the minus 1 times Garrett-Monk. Here's 10 to the minus 6 times Garrett-Monk. And what you can see here is, okay, so all of a sudden my x-axis is 20% smaller than the resonant wave and 20% larger. So this x-axis is much smaller than this x-axis is. And the two triads, the test wave would be resonant with a near inertial wave right here and a near inertial wave that's right there, but it's not phase locking on those waves, those resonant waves. It's phase locking around waves of this approximate resonant condition, where the phase speed is equal to the group velocity. And as I have turned this down, now this is at 10 to the minus 6 GM, I'm not seeing any transition to the resonant problem. So which is to say, you can take this finite amplitude theory and turn it down to really small amplitude. You'd hope you'd get the resonant paradigm out of it, but it doesn't appear that I can actually do that. Despite that fact, I'm going to do a second thing. And I'm going to look at moments of the test waves. So I'm looking in time how the mean wave number evolves, how its variance evolves. This should go out and have a square here. So this is mean wave number as a function of time for 10 to the 5th or so different test waves. And here is its variance as a function of time. The numerical simulations, the ray tracing is in black. The Fokker-Planck equation would predict that these first and second moments have a value that changes in time, and that is given by the green line. And the formula that's used for this green line is simply the resonant Fokker-Planck equation. So what you're seeing is the evolution of the spectral moments is actually well described by the resonant theory, even though phenomenologically you don't have the resonant paradigm. All right. So summary, this deterministic behavior, there's a transition to a bound wave behavior at extremely small amplitude. And what you're talking there is about wave packets. And when you do the stochastic simulations, there's no transition to a resonant paradigm. You're never being able to turn the amplitude down small enough to get there. In terms of closures, the fact that you don't have this resonant paradigm doesn't seem to matter terribly much because the moments of the spectral evolution are well predicted by resonant theory. That's really good news because it means you can write a closure, but it still haven't resolved why there is dissipation in the wave field. And the thing about the kinetic equation is that these are systems of coupled oscillators. Wave packets, you're dealing with the particle in a well. And if you wanted to get a closure for a particle, you would count the amplitude of the wave packet, the particles, times their velocity. Their velocity is the time rate of change of vertical wave number, and the time rate of change of the first moment. All right. Thank you. I'm sorry about that.
Yes, I do apologize again, but we're going to have to move on to the next speaker in the interest of time. Thank you, Kurt. Our next speaker is Jim Doyle, who's going to be talking about dynamics and predictability of deep propagating atmospheric gravity waves with co-authors Fritz, Smith, and Eckermann.
Thank you. So I'd like to thank the organizers of this session for the invitation to speak this morning in this session. I'd like to tell you a little bit about an upcoming program that we have that's called the Deep Propagating Atmospheric Gravity Wave Experiment that we're referring to as Deep Wave. I'd like to acknowledge my authors as well, Dave Fritz, Ron Smith, and Steve Eckermann. So in the last 5 years or more, we've had a whole wealth of satellite data that have become available that show us in great detail of the location and characteristics of gravity waves on the planet. And this is an example of some of the work that Steve Eckermann's done. This is the AIRS data set, and he's done a climatology from 2011 to 2003 to 11 shown here for July. And what it shows is a number of prominent regions of gravity wave activity as deduced from this 3 millibar level in terms of the temperature perturbations that were correlating with gravity wave activity. And what it really shows is a couple of very prominent regions, namely South America associated with the Andes, and also the region around New Zealand and Tasmania. And there's also some other islands that seem to excite these waves in the southern oceans. So this led us to down a path to propose a field experiment that was centered on the Andes and Drake Passage region in the Antarctic Peninsula that we called Sangria. And it turned out that this part of the planet is a very difficult place to operate a field experiment, particularly for aircraft such as the NCAR G5. So we've shifted our attention now to one of the other very prominent regions, which is over New Zealand and this area near Tasmania. And we think that this is a great place, a great opportunity, an ideal natural laboratory to study these deep propagating gravity waves. And it's a much more feasible location to operate a field experiment. So one of the really significant reasons that we're so interested in this deep propagating gravity wave problem is because these waves are so important for the vertical energy and momentum transport. And the outstanding issues for this are that the satellite data alone can't tell us all the information because the satellites are really blind to the shorter wavelengths in terms of the horizontal and vertical. Additional motivation for studying these waves include the parameterization of these waves. We know that GCMs are not high enough resolution to be able to resolve explicitly these waves, so we need to parameterize these. These parameterizations are really deficient in a number of ways, and we really need some new observations and modeling to be able to better represent these in these models and to improve climate and weather forecasts. So this figure on the lower right is a mean reanalysis for the southern hemisphere for the wintertime, and it shows in contours are the zonal winds, in color are the temperatures, and there we go. And so what it shows is the polar vortex here with the maximum around 50 kilometers above the surface. We can see the extratropical jet here, and we have, of course, the secondary circulation that's driven in part due to the gravity waves. And here comes our deep wave focus area extends in this region, and I was going to say, here's my cheap animation of the morning. And so this gives an idea of if we excite gravity waves in these regions, they're able to propagate to deep altitudes in essence because the winds are so strong and extend very, very high aloft. And so we think that this deep wave program is really in a position, in an ideal natural laboratory to study these major gravity wave influences from the surface to 100 kilometers in altitude. In particular, focusing, as I mentioned, over this region of New Zealand and Tasmania. So let me highlight a couple of differences in terms of the background state between the northern hemisphere and the southern hemisphere. So the zonal winds differ dramatically from the northern hemisphere in that we often in the northern hemisphere end up with a critical level somewhere above the extratropical jet stream. And of course, the critical level filters these waves and we don't see as deep of propagation. Where in the southern hemisphere, of course, we have this polar vortex and we're able to propagate waves to a much higher altitude. Additionally, over the region of New Zealand, it's a very prominent topographic barrier to the westerlies. And this is an area of the planet where we get a lot of very strong winds. And we're able to do some analysis with the ECMWF reanalysis. And this is the frequency on the right of the 700 millibar winds exceeding 15 meters per second. And this is over a 20-year period. And we find an average of at least 7 days per July month of this sort of launching potential that occurs over by these mountains in the South Island of New Zealand. So it's a very prominent gravity wave source. Just to highlight a few more of the characteristics of the waves from the AIRS data set, and these are just snapshots from particular days at high altitudes of 2 millibars. And first of all, on the left, we can see clearly the wave activity is more or less linked to the topography itself, very much mountain wave oriented. We can see other days when the topography seems to generate the waves and the waves extend downstream to the southeast. Clearly, there are other examples where there's lots of non-orographic waves being generated here in the southern oceans, south of New Zealand, south of the prominent terrain. And then there are days when we see not only generation near the topography, likely associated with the topography, but also lots of wave activity to the south as well, so it's happening from multiple sources. I'd like to say a little bit more about the case that I mentioned earlier in the previous slide where the mountain waves seem to be generated and propagate to high altitude, and we start to see some of the waves streaming downstream. In this example, we have an idealized model with a balanced jet. And the balanced jet here is shown on the right at the initial time, and this maximum is around 30 kilometers in altitude. And this is an XY view, and we have a Gaussian mountain and relatively uniform flow to the north of the jet. And what we find is at a 10-kilometer altitude, after 24 hours, we can see a nice wave that's generated in the lee of this Gaussian mountain. As we start going higher up, we can begin to see the wave begins to extend further into the shear. And so that by 25 kilometers, you can see the very asymmetric pattern that results where the wavelengths now are growing longer and more refracted by the vertical shear. In fact, if we look at the vertical momentum flux of the zonal wind component, we could see, and that's showed on the right, the vertical momentum flux here, we could see the tilt with height that occurs in this region associated with the refraction due to the jet stream. And so these are sort of the dynamical processes that we'd like to better understand more. Another aspect that we're looking at closely is the predictability of deep propagating gravity waves. And this is the example that I showed earlier where we have waves being generated by the South Island of New Zealand that are streaming to the southeast. We're able to do a credible simulation of those. This is the potential temperature perturbation at 7 millibars from a model after 24 hours, and that is a reasonable looking comparison. We haven't done a detailed comparison yet. And what we'd like to do is to be able to use an adjoint model to better understand the predictability characteristics and also be able to shed some light on the sources as well. So this adjoint is a fancy method to rigorously calculate the forecast sensitivity of some response function to the initial state. So we're looking at where in the initial state is most sensitive to metrics that would affect gravity wave generation. So here's an example where we have a nested model, 30-kilometer resolution on the outer mesh, 10 on the fine mesh, and we use this adjoint to calculate the sensitivity of the initial state to the final time wind speed in that red box, which would lead to wave generation over New Zealand. So that's actually associated with a trough in the the lower troposphere that is very important for the generation of the strong winds that occur that launch the wave packet. We can actually show that and sort of trace this forward in time now, beginning with perturbations that propagate from the coarse mesh to the fine mesh and create very strong wind speeds. You can see the scale, it gets rescaled, so 1 meter per second perturbations grow to something like 20 meter per second perturbations. So we want to be able to make the link between the predictability in terms of the weather and the predictability of these waves high up, and also be able to use these tools to look at sources of waves, not only orographic but non-orographic as well. So let me say a little bit about the instrumentation. So these are the proposed instruments that we have, and it's centered for deep wave, and they're centered on the G5, the NCAR Gulfstream 5. And first of all, shaded in gray here are the instruments that are existing now. So these are the facilities now available. They include the in situ instruments, dropsondes, and the microwave temperature profiler. The exciting aspect here is that we've proposed 3 new instruments that are being built, and this is being spearheaded by Dave Fritz and his group. And they include a Rayleigh LiDAR, a sodium resonance LiDAR, and a mesospheric temperature mapper. And these instruments will allow us to be able, for the first time, to follow gravity waves as they propagate from the lower part of the atmosphere all the way up through the stratosphere into the mesosphere and lower thermosphere. Just to highlight the altitudes that we'll be looking at with these different instruments as shown by these color bars, you can see lower atmosphere will have the MTP, dropsondes, and then we'll have the Rayleigh LiDAR as well as the Rayleigh LiDAR density and temperature sensors. And in the higher altitudes, we'll have the sodium LiDAR as well as some airglow temperature imager instruments as well. So we'll be able to have a very nice coverage of the 0 to 100 kilometer part of the atmosphere to be able to observe these waves as they propagate vertically. I'll say a little bit next about the experimental design. And so these circles that just popped on are the conventional radiosondes that are available in this area. And this is another advantage of this region versus the South America areas, that we have a very nice radiosonde network. We actually have a radiosonde at Macquarie Island that is a regular radiosonde in the Southern Ocean that could be very helpful for our purposes. We also are proposing to augment this network with a profiler upstream of the mountains. Our program will be centered in Christchurch on the South Island, and we'll have a number of types of flights that we'll perform. One is over the mountains, where we're continually monitoring the waves. We'll also be able to perform some surveys out over the Southern Ocean, for example. We'll also be able to sample waves over the North Island as well as generated by Tasmania as well. Those are all within reach. And also we'll have a number of a small set of flights that will go out and observe these regions where predictability issues are important. So we'll go out and drop sondes in these regions and then be able to observe the following day the gravity waves. So let me summarize. The objective of deep wave is to better understand, model, and parameterize gravity waves by observing and characterizing them over their entire life cycle. And we'll be observing in one of the planetary gravity wave hotspots, this New Zealand region. The measurement campaign is planned for June and July 2014. And we'll have some new instruments that will be able to allow us to observe in a way we've never been able to before. We'll have extensive modeling capability, and we have a whole set of national and international collaborators. And our science focus, we have a number of questions already set, and these are looking at tropospheric, stratospheric, and MLT gravity wave dynamics and characteristics, as well as theoretical and modeling issues. And I'll stop there. Thank you.
Thanks very much, Jim. Time for 1 or 2 questions. Yes, right here.
So what's the status of the campaign? Is it already approved by all agencies?
We haven't received the final approval yet from NSF. The experimental design was reviewed by NCAR, and it looks very favorable. It's gone to OFAP committee, and so they've done their review of it. So we haven't received the final word on it, but we're keeping fingers and toes crossed that this will happen. Yeah, so things look very good. One of our next hurdles that we'll have is to test the instruments in February. So there'll be a planned instrument test aboard the G5.
Any other questions? I'll just ask one briefly. I was wondering if you intend to use any of these cases to evaluate the ability of wave drag parameterizations to get things right.
Yes, okay, so the question was about gravity wave drag parameterizations, and that's a very big part of the focus of our program. And Steve Eckerman and to our group, to some extent, will be looking at that issue and trying to not only evaluate the current generation wave drag parameterizations, but also move towards sort of the next generation type of approaches too. So that's definitely one of the thrusts. Yeah.
Okay, well, we shall definitely be looking forward to hearing more about this in the future.
Thank
Okay,
you.
we'll move on to our next speaker now. Our next speaker is Albert Herzog, who will be talking about long-duration balloon observations of gravity wave momentum fluxes and intermittency over Antarctica with co-authors Alexander, Plugonven, Jutukov, and Kokoretz.
Is there a pointer?
Yes, there's a pointer right here.
Okay.
You have to squeeze it a bit tightly.
Okay. Hello, everyone. I would like also to thank the convener of the session for giving me the opportunity to present some results here, and also acknowledge my co-authors, John Alexander from Cora, my colleagues from LMD, and Philippe Coqueret from the French Space Agency who manage the balloon campaign. So I will be presenting some results obtained with observation made with long-duration balloon flights, and I will divide the presentation between a first part, which will be devoted to diagnosing gravity wave intermittency in the stratosphere, and the second part of the talk will be devoted to the recent results on momentum fluxes, also in the stratosphere. So the motivations are very similar to the previous talks. We know that in the atmosphere, gravity wave transport energy and momentum from the troposphere to the middle atmosphere. And in the middle atmosphere, gravity wave breaks, and they contribute to driving the Brouwer-Dobson circulation in the middle atmosphere and also the QBO in the tropics. The gravity wave scales are such that they are only marginally resolved in atmospheric general circulation models. And so their global effect need to be parameterized. But there are some simplification, or the parameterization are too crude in some respects. And one crude assumption is that some of the gravity wave momentum flux is associated with non-orographic waves, and there is no link or almost no link between the source and the momentum transported by the wave. So in this talk, we want to discuss this assumption, also to provide some constraint for gravity wave parameterization. All right, so most of the results here have been obtained with observation provided by those kind of devices here, which are long-duration stratospheric balloons. It's not classical radio sound balloons. Those balloons are made of plastic, so when fully inflated, they are non-deformable, and they can fly for a long time, up to 3 months or maybe 100 days in the stratosphere. They fly on constant density surfaces, and one of their great assets is that they are transported by the wind, so they behave as quasi-Lagrangian tracers in the stratosphere, which means that we have direct access to the intrinsic frequency of waves. And this is an important parameter to diagnose wave activity. We had two big campaigns up to now. The first one took place in 2005 and 2006, and 27 balloons were launched from McMurdo, Antarctica, which is around here. And you can see here all the trajectory of those 27 balloons. We collect meteorological observation we collected a meteorological observation every 15 minutes during those flights. And doing some correlation between those parameters here, we are able to derive the zonal and meridional momentum fluxes. we are doing a wavelet analysis to spot the wave in the time series. The recent campaign took place 2 years ago from the same station, McMurdo, Antarctica. The flight level were essentially the same in the lower stratosphere, but this time we have observation every 30 seconds, and I will show you the results at the end of the talk. Otherwise, the analysis is quite similar, and the trajectories also are very similar. So the balloons are mainly advected in the stratospheric vortex. All right, so I'll talk first on gravity wave intermittency with the oldest campaign. And to study gravity wave intermittency, we will directly look into the gravity wave momentum flux probability distribution function, PDFs. And we will also compare those balloon-borne momentum fluxes from observation provided by the Hurdle's instrument. So this is the PDF of the balloon in black and Hurdle's in red, momentum fluxes for October. And here, this is the PDF of the absolute value of the zonal momentum fluxes. So the first remark is that both kind of observation are completely independent, and still you've got very similar shape and amplitudes of momentum fluxes, which means that probably this is a real feature of the atmospheric gravity wave field. The other remark is that the mean value, and I hope that you can see it, but the mean value for those momentum fluxes is between 1 or 2 millipascals, which is around here, very near zero. And what you can observe is that there exists a very long tail of rare but very large amplitude events that we can observe in the atmosphere. And actually, if you look at the part of the momentum flux, which is due to only the 10% largest events, you can see that those events correspond for the balloon observation to momentum fluxes greater than 3.5 millipascal or 1.5 in Hurdle's, so approximately twice the mean value. And those 10% events explains up to more than 50% of the total gravity wave momentum fluxes. And more impressively, you can look at only the 1% largest events, and they can explain between 25 to 30% of the momentum fluxes. So a major part of the momentum flux is due to rare, large amplitude events. We have made a separation between what occurs or what is observed above mountains, which is the red curve here, and what is observed above flat areas like the Antarctic plateau or the ocean. And you can see that, as expected, the mean momentum flux is higher or larger above mountains, but also the intermittency of the wave flux is increased above mountains. And if you compare those two lines here. The difference with the previous plot is that here we are looking at the whole Vorkor campaign, so from September to January, so the momentum fluxes are slightly smaller than what we have seen before, but above the mountains, the 1% largest event can explain up to 25% of the flux. So not only the momentum fluxes are higher or larger above mountains, but the wave intermittency is also increased. On the other hand, you can see that on that part of the PDF, there is the momentum fluxes and the probability of occurrence are very similar. So there seems to be a background wave activity. All right, this is all I wanted to say for the intermittency. There is a JAS paper just published, and you can see more details in this paper. So now I turn to the most recent campaign, the Concordia-Z campaign. So with respect to Vorkor, there were two major improvements during this campaign. The first one I already spoke about is the higher time resolution along the balloon trajectories. And so this has an important consequences, and this is illustrated here on the plot, which is the intrinsic frequency spectrum of zonal and meridional velocity from one of these balloon flights. And you can see that we can, with those observations, high-resolution observation, we can now resolve the whole range of gravity waves from the inertial frequency to the Brand-Weissler frequency, and this is a relatively, well, it's quite new in the atmosphere. The other improvement is that we had higher precision measurements, especially for the altitudes provided by a GPS receiver and from the pressure measurements. And with these higher resolution measurements, we are now able to diagnose the pressure, the Eulerian pressure disturbance induced by gravity waves. And this is simply done by taking the observed, the Lagrangian pressure distribution disturbance, and subtracting the Lagrangian contribution, which is the vertical displacement of the balloon times the gradient of background pressure. And with this Eulerian disturbance, pressure disturbance, we can infer new parameters from the observation, like the horizontal intrinsic phase speed, the ground-based phase speed, and the vertical wave numbers. So first, I show the distribution, geographical distribution of the absolute momentum fluxes. So this is the flux seen. The flux in the direction of propagation of the wave. And this result is quite similar to what we had observed with Vorkor. So we do observe the large momentum fluxes above the peninsula and also above the Drake passage around here, and also above the Transantarctic mountain along the coast here and over there. There is also some enhancement of activity along the along the Antarctica coast around here and here, which is probably linked to katabatic wave generation by katabatic winds. On the other hand, you can see that the plateau is a region where the gravity wave momentum fluxes or activity is very small. And in particular, we see that above the ocean, we do observe more fluxes than above the plateau here. So the largest value we observed are above the peninsula here, the lowest here, and the mean value is here. We can do a zonal average and divide the flux between mountain and flat areas, and we do recover results very similar to what we had with Vorkor, and stressing the importance of non-orographic waves above the ocean here, which are with levels very similar to what we observe above the peninsula. We can divide those results. We can look at the zonal and meridional fluxes, and we do observe mainly negative fluxes, so westward propagating waves for the zonal component. But for the meridional component, there are positive and negative values, and positive values above the Antarctica, above the peninsula here, but negative values here, and it mainly depends on the wave, on the mountain range orientation. So some of the new results that we can have with the Concordia observation is, for instance, the distribution of the phase speed distribution of the zonal momentum fluxes, which is shown here in the intrinsic frame of reference here and the ground-based frame of reference. And you can see that most of the flux is found between 0 and minus 40 meters per second here, and between 0 and 20 meters per second for the eastward propagating waves. The ground-based distribution is more centered around 0. You can also see, interestingly, this secondary maximum here, which is actually due to the mountain waves. And this maximum is shifted toward very small values around here in the ground-based phase distribution. And the last result I wanted to show is the wave number intrinsic frequency distribution of momentum flux and kinetic energy. So momentum flux is here and kinetic energy is here. The vertical wave number is along the x-axis, and the intrinsic divided by the inertial frequency is here. And the thing that I wanted to stress is the fact that we observe the broader distribution of the momentum fluxes as compared to the kinetic energy distribution, which means that momentum a more important part of the momentum fluxes is associated with higher frequency waves. All right, so this is my conclusion, and I think I will stop here.
Thanks very much. I think, again, in the interest of time, we'll move on to the next speaker. And I'm going to relinquish the chairmanship now to Paul Williams for the remainder of the session.
Thanks, Jeff. Good morning, everyone. We're stepping up a gear now to faster talks of 12 minutes each, the first of which is given by Lars Hoffmann.
Okay, so good morning. My name is Lars Hoffmann from the Research Center in Jülich in Germany, and I'm presenting a study entitled A Global View of Stratospheric Gravity Wave Hotspots Located with Earth Observations. So this work was done together with Shanghui Xu from the University of Science and Technology of China and with Joan Alexander. Okay, so this is the motivation for the work. We want to know how do the global distributions of stratospheric gravity waves look like, where are the hotspots, and what are the sources of the waves. To study this, we used a 9-year record of radiance measurements from the EARTH satellite, or EARTH instrument aboard the Aqua satellite, and we studied the peak event frequency of the gravity waves. So we think that the results of this study can support the selection of promising regions and seasons for future case studies on gravity waves. So this picture shows you the measurement geometry of the EARTH instrument. You have the instrument 700 kilometers above the ground. So this is, okay, I don't find the point. Okay. So we have the instrument 700 kilometers above the ground. It uses a rotating mirror to do scans in the across-track direction. So we get scans of 90 footprints, and these cover about 1,700 kilometers on the ground. So within one day, you get this typical scan pattern. And this plot in the upper right, this shows the the resolution of the measurement. So the field of view is about 0.6 times 1.1 degree, which is about 14 by 18 kilometers at the ground. So these are examples of EARTH's radiance spectra. These are two spectra. So this shows brightness temperature versus wave number. And these are two spectra. One is for clear air, the red one. The other one, the blue one, is for a cloudy scene. And we use these measurements here at 2,300 wave numbers, or 4.3 micron, which is a CO2 fundamental band to detect the gravity waves. So here you can see we are sensitive to measurements only in the stratosphere. So these are the temperature weighting functions for these 4.3 micron channels. So you see we are most sensitive to temperature changes at 30 to 40 kilometers altitude. The full width half maximum is about 25 kilometers. And we are not sensitive to any temperature changes below 20 kilometers. So we are not affected by clouds or interfering species like water vapor. So this is a recipe to detect the gravity waves. As a first step, we calculate the 4.3 micron mean brightness temperature, which is based on 40 channels. So by averaging this large number of channels, we get a rather low noise in the result. It's only 0.03 Kelvin. And this is important because this helps us to be sensitive to vertical wavelengths which are shorter than 25 kilometers. Then as a next step, we fit and subtract a fourth order polynomial fit in the across-track direction to get brightness temperature perturbations. So this removes the limb brightening effect, and it removes slowly varying atmospheric signals, for example, due to planetary waves. And then as a next step, we calculate the local variance from the perturbations. So for each footprint, we calculate the variance sigma squared of all footprints within 100 kilometers radius. And then we apply simple threshold criterion then to detect a gravity wave. So we see if the variance is the variance which is composed of the gravity wave signal and the noise, if this is larger than a variance threshold sigma t squared. And now this variance threshold sigma t squared is selected as a function of latitude, month, and time of day. And I should mention, or this is important, and also a difference to the results presented earlier from Steve Eckerman, that we optimized our variance threshold to detect peak events. So if we look at the background variance and then we just see if the local variance exceeds this background signal, which indicates a very strong gravity wave event, then we just count these events. So this is an example. This shows 4.3 micron brightness temperature perturbations on the 1st of January this year at nighttime. You can see here a lot of gravity waves in Europe, over Russia, and then there's also like a band of gravity waves at 20 degrees south. Now this would be the corresponding local variances. And so here we just pick one threshold, or we pick a variance threshold to detect the gravity waves. So this is a plot of the variance threshold that we have selected for the peak event detection. So here you can see, for example, if you take the curve for December, you see that these take the background variability into account. So we can see two maxima. I think the pointer is, okay. There's like a maximum here at 20 degrees south, which we also saw in this plot before. There's another maximum here at 60 degrees north. So, and we just count the events which exceed this threshold values. So which wavelengths are detected? This is, or can be inferred with a numerical simulation with a radiative transfer model. So here we simulated airs measurements for different horizontal and vertical wavelengths. And then we applied our method to detect the wave. So we subtracted the background and computed the local variance. So these numbers are the local variances. And for example, if we have a threshold of 0.01 K squared, you can see that we are sensitive to vertical wavelengths down to 13 kilometers. And in the horizontal, we would be sensitive to wavelengths from 50 to about 1,000 kilometers. And this also shows you why it's important to average many channels, because in this we can go down to the shorter vertical wavelengths. So then how do we identify the hotspots? First we calculated seasonal peak event frequencies. So we analyzed the data on a fine spatial grid, 0.5 by 0.5 degrees. And then for each grid box, we get the number of peak events versus total number of footprints. And I'd like to mention that we got very good statistics here due to a long time series. So we analyzed 9 years of data. And in total, we analyzed data from 10 billion satellite footprints. Then to identify the hotspots, we used a simple threshold criterion. So we checked if the peak event frequency exceeds the 5% level. And then we apply a cluster algorithm to find the neighboring grid points of each hotspot. And what I also did in the paper is, which I cannot show here in the interest of time, is a classification of hotspots in terms of wave sources. So for airs, it's interesting that we can also get information or directly get information on convection. So we also calculated occurrence frequencies of convection from airs, which we use to classify the hotspots. And then for the orographic waves, I simply used global relief model data. Okay, so this is one of the results. These are the nighttime hotspots in boreal summer and austral winter. So if you can see the well-known hotspots like the Andes, the Antarctic Peninsula. You can also see these islands in the southern oceans, the Transantarctic Mountains, New Zealand, Tasmania. And on the northern hemisphere, it's interesting. So these are the mostly, I think, orographic features. In the northern hemisphere, you can see this big hotspots related to the thunderstorm season. So these are all convective waves. And similar here in Southeast Asia, there's also a convective hotspot. Okay, so this is now the opposite season. So these are the nighttime hotspots in boreal winter and austral summer. And here we find convective hotspots in South America, Australia. Then here in the northern hemisphere, we have all these orographic hotspots related to mountain ranges and orographic features like Scandinavia, the UK, the Andes, the Alps, sorry, the Ural Mountains, yeah. And then maybe a very interesting result of the study is that based on the large amount of data which we have analyzed and the high horizontal resolution, we were also able to locate a number of mesoscale hotspots which were not identified or not studied in detail so far. So these are the daytime hotspots in boreal spring and austral fall. And I just picked 3 of these mesoscale or small-scale hotspots as an example. So there's one here over the California Peninsula. There's another one here at the west coast of the Sahara. This is probably an interesting one because this is a rather flat area and no convection is going on. So this is probably related to land-sea heating contrasts. And another one is here at the Red Sea. This is also, I think, an interesting hotspot. There was recently a paper in nonlinear processes in geophysics which pointed out that this is a hotspot for trap waves in the troposphere, but we see it also here in the stratospheric data. So as a summary, these are the key points. A 9-year record of Earth observations was used to detect gravity wave peak events on a global scale. And many mesoscale hotspots were identified, of which several are unknown or only poorly studied so far. And we think that this study supports the selection of promising regions and seasons for future case studies on gravity waves. So there's a new paper in JGR which is in press now about this work. So thank you.
Thank you, Lars. We've got time for one quick question, if there is one. Maybe I can ask quickly. You mentioned in your detection recipe you used a 4th-order polynomial fit. Are your results sensitive to that choice?
Yeah, this is a bit as some people are using other fits, for example, a 6th-order polynomial. So I think there's not a big difference in these 2 methods in 4th order or 6th order. So I think it's not really important which one you choose.
Okay, thank you again. The next speaker is Marvin Geller. He's going to talk about a comparison between gravity wave momentum fluxes in observations and climate models.
Thank you. Squeeze that really hard. Okay. Not showing up at all. Really hard. Can't do it. If you press really hard. Okay. Okay. See, I'm having trouble doing this thing. I'm going to be showing today the results of a study involving several modelers and several observational individuals. So there are 11 co-authors representing 5 observational groups and 5 modeling groups. So that reduces to about a minute per group in this talk. So So the idea here is that, as we've heard, gravity wave fluxes are parameterized in climate and weather prediction models. And the parameterization, particularly in the non-orographic models, the part of the parameterization, the source function has been rather arbitrary in many cases. So here we're going to be using the, sorry I can't use this pointer, I just, oh there it is. Okay, so we're going to be using satellites, long duration super balloons, high resolution radiosondes, heard about this already, and three climate models with gravity wave parameterizations, and 2 models that seek to resolve planetary waves without such parameterizations. And this is the observational part here. So here we have 3 satellites, and then the Vore core that Albert spoke about. Note that the Vore core in red is only at 20 kilometers during that season. So what you see here, now, okay, so we've got latitude, South Pole, equator, North Pole, and we've got the gravity wave momentum flux. I should mention this is absolute gravity wave momentum flux, so we're summing the momentum flux in all cardinal directions, because the satellites in particular detect fluctuations, but they don't really get the direction of propagation. So to compare with the satellites, we're using absolute momentum fluxes. And I'd like to point out a few features. One feature is that the maxima, and we saw that in an earlier talk, we saw that tends to be in winter, January 2006. This is the year we chose for this. The highest numbers are in the northern hemisphere high latitude, winter high latitudes. So January, northern high latitudes, July, southern high latitudes. And there's an indication this maximum is bigger in the southern hemisphere, but some of that may be due to the satellite sampling. Another feature is that in the summer hemisphere, the momentum fluxes actually maximize around 20 degrees. And we saw that also earlier in some other data sets. And finally, if you look, you see that in the summer hemisphere, these fluxes tend to go towards 0. So these are just briefly, there's more information here which I'll show, but briefly those are 3 things I'd like to point out. And here are models. So these 3 are conventional models with gravity wave parameterizations. Canto and CAM5 are rather high resolution models that seek to get the spectrum. I don't think that, and this is at 20 kilometers, 40, same format as before I should have mentioned, 20 kilometers, 30 kilometers, 40 kilometers, 50 kilometers. And you see basically this is only averaged absolute momentum fluxes. And you see the same features. You see the maxima are at winter high latitudes. You see this subtropical maxima. But interesting enough, this is the Canto model here, which is resolving, does not have parameterization, and it falls off towards the pole in both hemispheres. But the models with parameterization do not show that feature. Their absolute momentum fluxes are not falling off towards the pole, as is shown in observations, and the Canto model, which is actually trying to resolve these features. So that's a difference between the observations and the models with parameterized fluxes. Now, this is actually the beginning of a story rather than the end of a story. This is the first formal comparison, as I said at the beginning slide. So one of the things we noticed quite rapidly, and I could have pointed out in the previous one, but it's shown more markedly here, here are globally averaged absolute gravity momentum fluxes for these models and also the observations. And you see here are the models that have gravity wave parameterizations. Here are the satellites, and this is the Canto model, and that's the CAM5 model. And you see that the satellite-derived momentum fluxes are falling off faster in altitude than the parameterized fluxes in the climate models. Now, the parameterized fluxes have been adjusted to get winds and temperatures that agree with observations. So there's nothing, and then they have a formulation. Interestingly enough, these three models use three different gravity wave parameterizations. ECOM used the Hines parameterization, Warner-McIntyre, and this was Alexander Dunkerton. So there's a variety of parameterizations here, but this is a rather robust feature. The satellite fall off faster. The CAM5 falls off faster, and that appears to be that is just a high-resolution model, a high-resolution version of a conventional climate model. So it's a rather low top. Its top is at 40 kilometers, and it has rather coarse vertical spacing and has essentially a sponge layer above about 25 kilometers. Now, given the difference in the height variation, these are maps for July 2006 at 40 kilometers for the, let's see, I'm reading the Canto, CAM5, GISS, ECOM, Hadley GCM, the Hurdles 1, a satellite, Hurdles 2, and Sabre, a satellite, at 40 kilometers. And what you see here, since it's July, you see these high resolution, and now they're all normalized essentially. They're showing the log of the term that would multiply the globally averaged momentum flux at that level, so that the maps can be easily compared. So up here, what you can't read are actually these numbers, but I'm looking at patterns here. You can see that the high-resolution models and the satellites showed maxima at high winter latitudes, as I mentioned before. We see this is also in the parameterizations, the models with parameterizations. But again, we see that, and we see these summer, low latitude, about 20-degree momentum fluxes in both the high-resolution models and in the satellite data. And these are associated with summer over the low-latitude continents. We also see, however, that in the high-resolution models and in the satellite models, in the satellites, there's very little flux at summer high latitudes, which is not always the case in the models with the parameterizations. Okay. This is a comparison that was set up for Vorkor, which was mentioned by Albert Herzog. And you see, for example, this hotspot over here from Vorkor, and you see Canto model, CAM5, and the GCMs. Interestingly enough, these high-resolution models, even though they're quite high resolution, are clearly not resolving the high frequency, the short wavelength gravity waves. In other words, there's a lot shorter wavelengths than what's resolved in these models. And there's also a comparison with high-resolution radiosonde data. This is actually July comparison, and this would be 20 kilometers from the models, some satellite data, radiosondes, and you see, for instance, from the high-resolution radiosonde, you see a clear signature of the Rocky Mountains, which doesn't show up so much in the, well, it just doesn't show up so much in the high-resolution models. So again, it sort of indicates that they're not resolving these short horizontal wavelength waves. So, the conclusions. The different methods of deriving gravity wave fluxes give somewhat different results. In other words, the Hurdles 1, I didn't dwell on this, Hurdles 1 and Hurdles 2 use the same data, but somewhat different methods to derive the gravity wave fluxes. And they get somewhat different results, and these are still being discussed. The satellite-derived momentum fluxes fall off faster than the parameterizations and Cantor model with resolved fluxes. This is likely due to sampling limitations. The maximum are seen in just about everything at winter high latitudes. They do not show the fall off in summer, and et cetera, et cetera. You can read as well as I can. So, some future directions. Clearly, the two of the models that I showed with parameterizations take globally constant source functions for gravity waves. So they should be improved. And of course, these satellites were not maximized or optimized for this purpose. So we can do better with satellite programs that are optimized for this purpose. Again, this is a first attempt, and you'll probably hear more. Thank you.
Thank you, Marvin. I'm afraid we need to move straight on in the interest of time to the next talk, which is given by Stuart Webster. He's going to talk about convectively generated gravity waves in the context of the Indian monsoon.
Okay, so this is the title of my presentation, and this work is part of an EU-funded project called Embrace. And I think to start with, I should thank the conveners for ordering the presentations as they have, because Marv's final point was about trying to improve the representation of the source of gravity waves in GCMs, and that's really what the aim of this study is all about. So we're looking at the Indian monsoon, which, as Lars pointed out, is one of the convective hotspots for gravity waves, and really we're aiming to try and link our convection parameterization to the source for the middle atmosphere gravity wave drag parameterization. And in this talk, I'm just going to focus on point two, which is we're going to try and improve our understanding of the convectively generated gravity waves through evaluating the characteristics in high-resolution explicit convection simulations. And so in this study, we're really looking at limited area model simulations of the Indian monsoon. We're going to do a wide range of horizontal resolutions from 1.5 kilometres up to 120. So the details of the simulated period are essentially it's a 3-week run of last year's Indian monsoon. And the main point is actually, well, it's a 3-week simulation. It's not actually important to this talk what that time period was, but if you look at my poster tomorrow afternoon, I think it is, then actually you'll see more details of the tropospheric behaviour and why we've chosen this period. And the essential details for the driving model are that we're basically trying to constrain our limited area models with as realistic as possible lateral boundary conditions. So yes, we've got a wide range of horizontal resolutions for our limited area model simulations, going from about 120 kilometres for the climate-like simulation down to 1.5 kilometres. The model domain is shown on the top right, and basically all the limit area models span the same domain, and they're all nested directly inside the global forecast model. And this actually does include the 1.5 kilometre model, so there's a factor of 16 jump in resolution, and that's even with the fact that Tibet is in the northern boundary of the domain. So in the boundary, the terrain heights go from about 0 to 6 kilometres over just a few grid points. But basically all the limit area models are initialised with the same data. They're all driven with the same lateral boundary conditions. And so this really gives us as clean an assessment as you could hope for, I think, to study the impact of the horizontal resolution. So the focus of the presentation is going to be on this explicit convection simulations. So we look at the 4 kilometre and 1.5 kilometre simulations. And these are configured identically, except for the horizontal mesh size. So we use 118 levels in the vertical. So this is building on our fine resolution, tropospheric resolution that we have in our operational forecast models, explicit convection models for over the UK. And we basically raise the model lid up to near enough 80 kilometres, and we keep a reasonable resolution in the stratosphere to at least do a reasonable representation of the stratospheric wave field. We use a very short time step of only 10 seconds because we've got a semi-implicit, semi-Lagrangian advection scheme in the unified model, and we need that short time step to minimise the damping of the gravity wave field. So, first off, actually show you what we actually get from running at the high resolution, the 1.5 kilometre model resolution, compared to what we get from our global NWP resolution. How can I click on that link? Illustrate that. That's marvelous. So, okay. Escape. Okay. Phew. So the top right, we've got the top row is showing the behaviour of the global forecast model every 20 minutes. Sorry, every hour. And this is a week of simulation. And the bottom row is showing you what you're getting from the 1.5 kilometre model for the same period. So the things you can see are that the rainfall is very grid scale in nature, both in time and space, with the NWP forecast model. And you also see that the peak in the convection is about 7Z, which is local noon. So in other words, there's a systematic common bias to convection parameterizations where the rainfall is a maximum at local noon rather than in the early evening. With a 1.5 kilometre model simulation, you see much more spatially and temporally coherent rain cells, and in general they're moving eastwards over India, so being a vector with a low-level flow. And if you then go to the OLR, you can see that actually you're capturing quite well the complex sheared environment of the Indian monsoon because the actual clouds are tending to drift off westwards. So the 1.5 kilometre model permits much more realistic convection with convective cores of typically 30 metres per second or even more. And as a result, we should have a qualitatively realistic wave field aloft. Yesterday. Okay, so now actually we want to look at the flow features of the high-resolution simulations. So we're actually going to look at the high time-frequency diagnostics we've got out from these simulations, which is every 5 kilometres in the vertical from 5 through to 40 kilometres. We've actually got out winds, potential temperature and density every 2 minutes for the 3 weeks of simulation. So far I've actually only looked at 1 day's worth of data. And that's basically because with a mesh size of 3,000 by 3,000, that's still about 300 gigabytes of data for 1 day. I've actually looked at a day, a couple of weeks into the simulation. And now we're going to have the same problem again. So, yeah, let's get. So if we go to. So this is showing you an animation of the flow field every 10 minutes for this day. So top left panel is the vertical velocity in colour at 5 kilometres, and then it's 10 and 15 going down the left column through to 40 kilometres middle right, and then below that you've got the surface rainfall field. So really, and the arrows are showing you the horizontal wind field. So basically here the vertical velocities are due to convective updrafts. You get to 20 kilometres and you're above the tropospheric convection, and you get a minimum in the wave amplitude before the wave amplitude increases as the density reduces. And so really what you see, particularly if you get up to 40 kilometres, is concentric semicircles, I guess, of the vertical motion. And I guess that really is due to the critical level absorption from the westerlies at 20 kilometres. I don't think I'm going to... Yeah, I'm going to have to go for that one first. So this is then showing you the same things at 4 kilometre resolution, and if you've looked at these animations as much as I have, you see the real differences are but most of the features are the same, but the wavelengths tend to be slightly longer, and actually the actual peak amplitudes are less, as you might expect, than the 1.5 kilometre model. This worked fine when I was testing it yesterday, I assure you. Okay, so from those animations, I would say the critical level filtering is very obvious, and there's fairly, what you might anticipate, differences in the wave field due to the difference in resolution. Certainly consistent with more idealized studies such as that by Laneham and Creve 2008. I guess the actual bottom line up to all this is the differences in the 4 and 1.5 kilometre model wave field just remind us that actually even the 1.5 kilometre model is only permitting gravity waves. So you probably need to go down to order 100 metre resolution to be properly resolving the convective updrafts, to then have a chance to properly resolve the stratospheric wave field and the momentum fluxes. So even at 1.5 kilometre model resolution, I would say you really can only expect to find a qualitative link between the stratospheric wave field and the tropospheric convection. If we actually look now at some of the wave measures, the wave field, actually just look at the bottom animation. Here we go again. Get out of the way. So this is showing the hourly averaged momentum flux amplitude from the 1.5 kilometre model simulation. And basically what you're seeing is that reassuringly the wave amplitude is decreasing with height. And other features, you can see there's large wave amplitude here, which is gone by 30 kilometres, so we're getting wave filtering going on there, and there's less wave filtering over India. So you're getting realistic light behaviour in the way the waves are being dissipated. That was the last animation, you'll be pleased to hear. Okay, so just looking now, this says hourly average fields, but this is actually instantaneous time series through the day of the vertical velocity amplitude. So both models show a peak in the amplitude at 10 kilometres, so the thick red line, a minimum above the tropospheric convection at 20 kilometres, a thick green line, and then above that, you see the wave amplitude increase through to 40 kilometres. You get an interesting signal in the 4 kilometre simulation where you've got the peak amplitude is at 10Z at 10 kilometres, but actually it takes about 4 hours for that peak amplitude to reach 40 kilometres. Unfortunately, the 4 kilometre model doesn't look like it's behaving anything like the 1.5 kilometre model, because the peak amplitude of the diurnal cycle is bang out of phase. So that, I guess, suggests the 4 kilometre model simulation is not a numerically converged solution, because if it was, it'd look a whole lot more like the 1.5 kilometre model simulation. And I guess the final point is that the amplitudes, the vertical velocity amplitudes are larger at all levels in the 1.5 kilometre model, as you would hope, with a finer vertical horizontal resolution. And the main point from the momentum flux plots is that the time series shows that although the vertical velocities are larger in the 1.5 kilometre model, the actual momentum fluxes are smaller, as you would see if you just look across at the 40 kilometre level averaged over the day. So the dashed line there is the 4 kilometre model. So in other words, the diagnostics of the gravity waves are consistent with the shorter horizontal wavelength, faster vertically propagating waves in the 1.5 kilometre model simulation. So there's a summary, and I would guess that the main point is probably not even, for the UM at least, the 4 kilometre model is probably not even a viable, relatively cheap alternative to running at 1.5 kilometre model resolution. And indeed, it begs the question is how qualitatively converged is the 1.5 kilometre model simulation? And we intend to investigate this by running relatively short period, relatively small area, but a couple of 100 metre horizontal resolution simulations. And final point, don't forget to come and look at my poster tomorrow. I'm sure it's tomorrow afternoon. This is not the final version of the slide, anyway. So yes, so the tropospheric behaviour of these simulations is in the poster that I've got tomorrow morning. So thank you very much.
Thanks, Stuart. Thank you, Stuart. I can see hands up, but I'm afraid we need to move on because we're a bit behind schedule. Stephanie Evan is the next speaker. She's going to talk about convectively generated gravity waves in opposite QBO phases.
Thanks. So first, I would like to acknowledge my co-authors on this work, John Alexander from Cora and Jimmy Ludia from NCAR, for their help on this work, which focuses on gravity wave forcing of a QBO. And I'm going essentially to present some results of a paper which was published this year in JGR. So first, just a little bit of motivation and background for this work. So as you all know, the QBO is an oscillation of a zonal wind in the equatorial lower stratosphere. And it's a dominant source of variability in the stratosphere, and it's also important for the transport of ozone and water vapor that are influencing the climate. And we know that the mean ascent associated with the bryodopsin circulations slows down the QBO descent. The QBO is an important phenomenon, but it's still challenging for most climate models to simulate the QBO because first they don't have the good representation of convection, which is the wave source in the tropics, and also they can't resolve or parameterize the broad spectrum of waves which are needed to generate the QBO, and this can be the planetary scale waves such as Kelvin waves or the smaller scale gravity waves and inertial gravity waves. And most of the time, these models have to parameterize the effect of gravity waves and inertial gravity waves. And because we don't really know what is the forcing coming from these waves, so the focus of this work was to establish the wave forcing of a QBO associated with gravity waves and inertial gravity waves. So for that, I'm using a regional version of the WRF model, and most of my results here are going to be focused on the equatorial belt. So everything that I'm going to show has been averaged between 10 degrees south and 10 degrees north. So this is the configuration of WRF that I'm using. This is a tropical channel model. So it's a tropical channel because it's the model domain covers the global tropics. It has periodic boundary conditions in the east-west direction, and in the mid-latitudes at plus north at plus minus 42 degrees, the boundary conditions are given by the ECMWF reanalysis, and the model domain with spacing is 37 kilometers. And so we showed that this configuration of WRF was able to resolve gravity waves, observe gravity waves, and the convection in these two papers, one in JAZ and the other one in JGR. So this is showing the structure of vertical grid in WRF and in ECMWF. So this plot is showing the vertical grid spacing in kilometer as a function of altitude for WRF in red and ECMWF, the model which is used to generate the reanalysis, in black. So essentially above 30 kilometers, I have a dumping layer to avoid any wave reflection, and below 30 kilometers or so, which is my region of interest, I'm using a grid spacing of 500 meters. And this is a higher resolution than ECMWF because we want WRF to be able to resolve the vertical structure of gravity wave and their propagation and effect in the stratosphere. And we actually proved that it was able to reproduce observed gravity waves in this JAZ paper. So the data that I'm using correspond to the ECMWF reanalysis, the ERA interim reanalysis, which are available every 6 hours. So this is how often also I update my boundary conditions in WRF. And I should precise that I use the ERA interim data on the original model level so that we can get, keep enough resolution for the initialization of WRF. And so to validate the model representation of precipitation, I'm using the TRIM satellite precipitation data. They are available at a quarter-degree resolution, so I interpolated them to the WRF grid to do the comparison. And so here on this plot, you can see the evolution of the zonal wind in the era interim from November 2005 to March 2007. And so what we did is that we did simulations for 2 months, the month of January 2006 and the same month in 2007. So they correspond to periods with a similar regime of convection, so the Australian monsoon, and but they correspond also to periods with opposite QBO phases, so westerly shear phase in 2006 and easterly shear phase in January 2007. So first, what we did was a validation of a precipitation variability in WRF, because this is important for wave generation. So you can find more details in the paper, but basically what we found is when you look at this table, when you look at the precipitation variability for TRIM and WRF, they both agree pretty well. So it shows that for both simulations, WRF was able to produce precipitation variability comparable to TRIM. And so this gives us some confidence in the model ability to generate wave by convection. So this is showing the evolution of the mean zonal wind in WRF. That's a plot in the center. In era interim, that's a plot on the right, and the reducing data, which is the plot on the left. So the black line corresponds to the mean zonal wind in January, and the red corresponds to the wind in February. So in 2006, when you look at WRF in the center, what you can observe above 25 kilometers is a descent of the westerlies. And when you compare that to the evolution of the radius data, the wind in the radius data, you can see that WRF can reproduce the descent of the westerlies, which is observed in the radius zone. And it can actually do a little bit better than era interim. And when you look at the same evolution in January 2007, you can see that from January to February 2007, you mostly see an acceleration of easterlies, and the amplitude of the acceleration is WRF is in good agreement, is actually in better agreement with the radius on data compared to era interim. So from these plots, what we can say is that WRF agrees pretty well with the radius on data for the zonal wind evolution. So we can say from that the gravity waves generated in WRF can drive a large fraction of the QBO wind evolution. Another thing that we checked in the model is the reputation of tropical mean ascent, because this is important for the zonal wind budget analysis. And what we found is that above 18 kilometers, so which is again a region of interest, WRF and era interim show estimates of tropical ascent which are in agreement. And they're also in agreement with the observations from these 2 papers, Mott et al. And Mark Schoberer et al. So this is an analysis of the zonal wind budget in the 2006 simulation. So this plot is a bit complicated, so let me just walk you through that. So here you have the wind acceleration due to planetary wave. This is a green curve. The wind acceleration from the gravity waves in red. And the blue term corresponds to the effect of the vertical advection, so the effect of a Bouillard-Hobson circulation. And the dashed black line corresponds to the wind tendency from the WRF simulation. And the solid line, the solid black line, corresponds to the total forcing, which is just the sum of the wave and advection terms. So when you look at the green curve and the red curves, what you can see is that they show similar amplitudes around 26 kilometers, where you have a peak in the wind acceleration. And so from that, we were able to conclude that during the westerly shear phase in January 2006, planetary waves and gravity waves contribute almost equally to the total wave forcing. So this is the same plot for the easterly shear phase of a QBO in 2007, in January 2007. And I should also emphasize that during January 2007, there was a steadying of the QBO winds. So that's why the wind acceleration, the black lines, that's why the acceleration is weaker. But when you compare the green and red curve, you can see that the effect of planetary wave is pretty small. And most of the balance is between the gravity waves and the tropical upwelling. And we found that during the easterly shear phase, the planetary wave contribution was really small, and most of the wave forcing, up to 80%, was coming from the gravity waves. So we can compare these results to this recent study by Kawatani et al. So basically they use a high-resolution climate model with no gravity wave parameterization, and they tried to simulate the QBO. And they were successful at getting a QBO without any gravity wave polarization, although the QBO had a period shorter than the one observed. But basically, what they found is that during the westerly phase, so this is the plot at the bottom, Kelvin were responsible, were contributing to half of the forcing of the QBO, and the rest was coming from gravity waves. So this is equivalent to what we found for January 2006. And during the easterly shear phase, most of the forcing was coming from the gravity waves. So again, this is similar to what we found for January 2007. So what we can say is that our results are in good agreement with the study, although we didn't use the same type of numerical models. So in conclusion, I would say that by using this WARF simulation, we were able to provide an estimate of gravity wave forcing of a QBO. And this is something that I didn't show in my talk, but which is explained in the paper. We also found that intermediate scale inertial gravity waves, so with horizontal wavelength greater than 1,000 kilometers, but with short vertical wavelength, were important for both QBO phases. And we argue that they should be parameterized in climate models to get a realistic representation of a QBO. Thank you.
Thanks, Stephanie. I'm afraid once again we need to move straight on to the final talk given by Bob Vincent about gravity wave generation by convection and the middle atmosphere response.
Where's the button? Yeah, okay. Can you go back to the first slide, please? Thanks. Well, it's well known that gravity waves drive the upper branch of the Breuer-Dobson circulation, and the wave driving must come from an aggregation of a large number of unknown number of gravity wave events. Here I want to talk about one gravity wave generating event, and specifically by convection, and look at its response in the mesosphere, near the mesopause. So the particular event that I want to talk about was observed during the TWP ice campaign in January, February 2006. Where's the... Okay, thanks. Not hard enough. There we are. So I'm going to talk about a single storm and bring together observations and modeling to describe the response. So the basic technique used a number of instruments. It used a weather radar, CPOL, which scanned from near the ground up to 18 kilometers over about a 10-minute interval. That measured the reflectivities from hydrometeors. And that was used to seed a high-resolution numerical model generated by Joan Alexander. That generated the gravity waves, and the waves then propagated. We'll talk about the propagation of the waves up into the mesosphere, where they were actually observed using a meteor wind radar. So the event that I want to talk about took place on 23rd of January. It was the largest mesoscale convective storm of the whole campaign. Gave rise to the largest rainfall event, and it had quite a large impact on the northern Australian monsoon. So the two plots on the right show sea pole soundings. This is a scan as a function of time and height over a particular radar site. And the main event that I want to talk about was concentrated near 18 UTC. On the right-hand side, you see a plan in space at 1 kilometre altitude, centred on this 18 UTC, and you can see that the storm was aligned essentially northwest-southeast at that particular time. So the gravity wave fluxes that we're going to talk about were derived from a dry, nonlinear, non-hydrostatic model, and the convective heating that went into the model was derived explicitly from the sea pole reflectivities converted to effective rain rates and latent heat result. The scale, resolution of the model was 2 kilometres in the horizontal and 0.25 kilometres in the vertical over this 400 kilometre grid. So the top panels show two different cuts of the gravity wave spectrum at 18 UTC at a height of 20 kilometres, which is the upper boundary essentially of the model. The waves are propagating eastward. This is a function of wave number, and on the right, a function of phase speed. And the bottom two panels show the spectra in more simple form. The waves are dominated by scales the order of 50 kilometres wavelengths, and phase speeds between 25 and 50 metres per second. So now we have to couple those waves, which are launched into the lower stratosphere at 20 kilometres, up into the mesosphere where we can actually observe them with the radar. We're provided a momentum flux spectrum, which is a function of horizontal wave number, function of ground-based frequency, and direction of propagation. And for any spectrum, which is over a 2-hour interval, overlapped by 1 hour, so we have a moving set of spectra, we get 27,000 approximately values of momentum flux with the appropriate resolution. We want to now trace these waves up into the mesosphere. So you have to give the waves the appropriate amplitude. If you launch them with the amplitude derived just straight from the spectrum, they'd have such a small magnitude that if they propagated without any kind of critical level interaction, they'd have very large amplitudes in the mesosphere. We have to remember, of course, that in reality, the wave fluxes emerging from the stratosphere into the stratosphere are localized in space, and this shows a plot of the localization just north of Darwin at 18 UTC. Of course, we know that in any convective event, there are very localized plumes with temporal variability on the order of minutes to tens of minutes at most. And so we've got to account for not only the localization, but also the temporal variability of the wave fluxes. So what we do is apply a stochastic approach, randomly launching waves in space and time in a given 2-hour interval. So now we've got to scale our wave amplitudes to ensure realistic amplitudes in the MLT. So we scale the wave amplitudes at launch by some initially unknown numerical factor, let's call it f. Ray trace each packet, each one of these 27,000 values of momentum, recombine them in the MLT, divide by f to preserve the total flux. You can look at these as basically a version of the Alexander and Dunkerton parameterization scheme, at least the approach they use. And then we compare the fluxes with what we actually observe using meteor radar, both as a function and time, function of height and time. And then we iterate f until we get satisfactory agreement. The ray tracing scheme that we used, by the way, was based on the classic paper of Marx and Eckermann. Once we've found a value of f, which actually turned out to be a factor of the order of 500, we could then relax the limitations and then randomly launch waves anywhere within this region and anywhere within a 2-hour interval and get some idea of the uncertainties in the ray tracing. To satisfactorily ray trace the waves, of course, you need a suitable background model of the winds and temperatures in the middle atmosphere. This is a composite from many observations during this very intensive TWP ice campaign. The main point of interest here are the very strong temporal variability due to the atmospheric tides up in near the mesopause region. Over this 8-hour interval, you can see the tidal winds reversing direction in both the north-south and east-west directions. So, after doing the ray tracing and comparing the observations, the black line here shows the observations from the radar with its uncertainties as a function of time. The red dotted line shows the results of the ray tracing, again with its uncertainties or the stochastic variations. So you've got the peaking at about 20 UTC, that is about 2 hours after the main event. And this shows the profile as a function of altitude. For comparison, by the way, this dashed dot line here shows the effects as if there would be no wave dissipation. Quite clearly, the wave amplitudes are growing much smaller than the e to the z upon h effects due to no damping. So there's quite clearly very strong wave dissipation going on in the mesosphere. This shows on the left-hand side the momentum flux as a function of phase speed, ground-based phase speed. It's the aggregated results from all the ray tracing measurements. And you can see that there's a very most of the momentum flux has been depleted, particularly that going towards the west by critical level interactions in the stratosphere. And on the right-hand side, we see the geographic variation of the momentum flux, primarily located just north of the Tiwi Islands, north of Darwin, in a region which is about 200 kilometres in extent. This shows the flux divergence, again derived now directly from the ray tracing. We've calibrated, so now we can have the momentum flux divergence in the east-west and north-south directions. Here's the resulting body force, and on the right-hand side we see time-height cross-sections of the body force. You can see its accelerations of the order of 200, 300 meters squared per second, lasting for about 2 or 3 hours. So in summary, we've got momentum flux deposition by wave generation, sporadic, it's localized, very large body forces, but for only 2 to 3 hours duration, over a depth the order of the scale height, and horizontal scales the order of 200 to 250 to 150 kilometers in space in the horizontal. And just to put these results in context, there's a paper by Pope et al. Which looks at how many metre-scale convective storms exist in the wet season, the tropical monsoon over northern Australia between November and April. There are about 12 complexes, storm complexes per day over this geographic region. This has implications, for example, for GCMs. If you look at a WACCM model, for example, a grid box is the order of about 1 to 2 degrees in latitude, longitude. That means about one storm complex every 10 days. And these results also have implications for in situ generation of transient tidal motions and secondary gravity wave generation. Thank you.
Sorry? Thanks very much, Bob. Just a quick reminder that the poster session is tomorrow morning, I think, between 8 and 12. And just as a suggestion, if you could be by your poster in the first half of that session, we're trying to cluster the author in attendance times between 8 and 10, just if you're able to do that. One final thanks to Jeff and Joan, the co-conveners, and I'd like to just end by thanking all the speakers once again for their contributions this morning. Thank you.